Okay, in today's lecture, we're going to cover the first part of the section 5.4 material on triple integrals. So this will be pretty similar to what we saw in the first part of chapter 5, where we were introducing the double integral of a function of two variables over some plane region. So here we're just extending that definition to a function of three variables. So we'll start by defining it over boxes, much like we did for double integrals. We started by defining them over rectangular regions. So to introduce the concept of a triple integral, let's suppose that we have a function f of three variables, x, y, and z, which is defined on a closed box. So some closed box in space, which we will denote as capital B. And it's defined as the Cartesian product of A, B, C, D, and R, S. So what that means, it's the set of all points x, y, z in space, such that x lies in the interval from A to B, y in the interval from C to D, and z in the interval from R to S. So just like we did for double integrals over rectangles, we could partition each of these intervals, A, B, C, D, and R, S, by choosing partition points, x0, x1, x2, and so on, up through xl, that lie within the interval from A to B. We could choose y values, y0, y1, and so on, up through ym, that lie within the y interval from C to D. And we would choose z values, z0, z1, and so on, up through zn, that lies in our z interval from R to S. So just like we saw for double integrals, where we were partitioning our rectangle into little sub-rectangles, by partitioning the x, y, and z intervals, we are partitioning our box B into sub-boxes, and there are L times M times N. So L, M, and N were the number of partition points that we were choosing, so we're partitioning our box B into these sub-boxes. And the notation that we would use for a particular sub-box would be B sub I, J, K. So this is the one where the right endpoint for the x interval is xi, the right endpoint for our y interval is yj, and the right endpoint for our z interval is zk. So down here in our figure, we had some box B, and then by partitioning our x, y, and z interval, we see that we're dividing up into these little sub-boxes, and any one of these sub-boxes we could identify by using the subscripts, B sub I, J, K. Now, what we're going to need is the volume of the sub-boxes. So just like for double integrals, we were calculating the area of our little sub-rectangles. So here to find the volume of our sub-box, let's let delta x sub I be the length of our box in the, or sub-box in the x direction. Delta sub yj be the length of the, or let's say the width of our box in the y direction, and then delta z will denote the height of our box in the z direction. So then the volume, not area, but volume of the box B sub ijk is denoted as delta V sub ijk, and it would be the product of its length, width, and height. Once we have the volume of each of our particular sub-boxes defined, we're going to choose some representative point, x, y, z, sub ijk star, in each of these sub-boxes. So the subscript ijk denotes which box we're choosing our point in. We use a little star superscript to denote our representative point. And we're going to form a triple Riemann sum, which is defined as evaluating the function f that we're working with at our ijkth representative point, and then multiplying by delta v sub ijk. That is the volume of that box where we chose our point from. And then we're going to do that for every box and sum that product over all such boxes. That is summing over the x, y, and z partitions. We're adding up this product for all of our boxes. So to define our triple integral, we have to introduce a norm. We're going to let this expression denote the norm of our partition P of the box. And the norm of our partition will be defined as the length of the longest diagonal of our sub-boxes. So when we're partitioning this box into little sub-boxes, different ones may have different length, widths, and heights. And the norm of our partition is going to be the length of the longest diagonal through any of these boxes. We can note that if we are shrinking the partition, or the norm of our partition, to 0, that means that we have a finer partition of our box. We're dividing it up into smaller and smaller sub-boxes. With this information, we can define the triple integral of the function f over the box B as follows. So the notation is similar to double integrals. We have 3 integral signs with the subscript b to denote the box that we're integrating over, of the function f of x, y, z dv. So we would say with respect to volume. And this triple integral will be defined as the limit of that triple Riemann sum as the norm of our partition approaches 0, provided that that limit exists. And if this limit exists, then our function f is said to be integrable over that box. So of course, when we were working with functions of 2 variables over subrectangles, we could use a Riemann sum approximation to approximate the value of the double integral. And we saw that it's sort of tedious. So in the case of 3 variables, it would also be very tedious. So instead of using this limit definition of a triple integral to calculate the value of a triple integral, we can make use of iterated integrals, much like what we saw for double integrals in our earlier work. So here, I'll mention the practical method for evaluating a triple integral is to express them as iterated integrals. So we have a theorem, which is sort of the analog to Fubini's theorem for double integrals. So this is called Fubini's theorem for triple integrals. And it says, as long as we have a function f which is continuous over a box B, then the triple integral of that function with respect to volume over that box can be expressed as the iterated integral of our function f of xyz in the order dx, where our x values were ranging from a to b over this box. Then with respect to y, where our y values were ranging from c to d, and then with respect to z for our outer integral, where the z values were ranging from r to s within that box. So Fubini's theorem says we can evaluate these triple integrals over boxes by expressing them as iterated integrals. And in the last part of our theorem here, it says there are 5 other possible orders of integration that all give the same result. So just like Fubini's theorem for double integrals said, well, it doesn't matter if you integrate in the order dx dy or dy dx. For triple integrals, there's a total of 6 orders of integration. We could have, for instance, dx, dz, dy, dy, dx, dz, dy, dz, dx, and so on. So grand total of 6 possible ways that we could order these differentials. And regardless of the order in which we integrate, we are guaranteed we get the same result using Fubini's theorem. So let's look at an example of calculating a triple integral over a box, and then we'll talk about how to integrate over more general regions in space. In this first example, we are asked to integrate the function 8x squared y z cubed with respect to volume over the box B, which is defined as the Cartesian product of -1, 2, 0 to 1, and 1 to 2. So here, Fubini's theorem that we just reviewed said we can express this in terms of an iterated integral, and it doesn't matter what order we integrate in. So here, this triple integral over the box B of 8x squared y z cubed dv, we can express as an iterated integral where my outer integral, I'm going to start with x, so we'll go from -1 to 2. Our second integral with respect to y, so from 0 to 1. And then with respect to z for the inner one, our z interval was from 1 to 2. And here our function was this 8x squared y z cubed. And here the order that I've set this up in would be the order dz, dy, dx. Now you can order this however you like and see that you get the same result if you want to try a different order. So here, starting with the innermost integral with respect to z, well, we would find our antiderivative with respect to z. So here we have z cubed. Its antiderivative would be 1/4 z to the 4th, but with our constant 8 out in front, the antiderivative of this 8z cubed will give us 2 x squared y z to the 4th power, where we're evaluating with respect to z from 1 to 2, and then in the order dy dx. So here, evaluating this inner integral at the endpoints, let's see what we have. So we have a z to the 4th term. If I evaluate at z equals 2, I've got 16, and then I subtract what I get when I evaluate at 1, which would be 1. So my 16 minus 1 for that term leaves me a constant of 15. So multiplying that constant by my 2x squared y, we have 30x squared y. And then we're integrating with respect to y, and then with respect to x. So finding the antiderivative next with respect to y, we have the integral from -1 to 2 of, for 30x squared y, we would have 15x squared y squared, evaluating from y equals 0 to 1, and then integrating with respect to x. So here again, if I'm evaluating y from 0 to 1, well, when I plug in 1 for this y squared, we have a 1, minus when we plug in 0, we get 0, so the difference of those values is 1, times my 15x squared that we're then integrating with respect to x. So for our last integral, our antiderivative is 5x cubed, which we're evaluating from -1 to 2. So we have our constant 5 times when we plug in 2 for x, we have 8, minus when we plug in -1, we get -1. So minus the -1 becomes +1. And so we're left with 5 times 9, or 45 for the value of that triple integral. So we see in this first example that evaluating triple integrals over a box is just like evaluating a double integral over a rectangle. We just have one extra integral to evaluate. So in the next part of this section, we're going to extend the definition of a triple integral to include integration over solid regions which may not be a box. So just like we saw in the case of double integrals earlier in our chapter 5 material, we first define them on rectangles and then over bounded plane regions, maybe regions bounded by two curves. So that's what we're going to introduce next for triple integrals. We want to extend our definition to include regions of integration, which would be any bounded solid region of a more general shape, not necessarily just a box. So just like we had for bounded plane regions, we saw we could describe them as type 1 or type 2 regions. So for bounded solid regions in space, there are three types or three classifications for these regions. So let's go through each of these. So here, our first one, we would say a solid region is said to be of type 1 if it can be considered as lying between the graphs of two continuous functions of x and y. So that is if our region E could be described as the set of all points x, y, z, where the z values are bounded above and below by two functions of x and y. That is above and below by two surfaces, where the points x, y are in some region D, which would be the projection of E onto the xy plane. So here in this figure, we show an example of a type 1 region, E, shown here in blue. It is bounded below by some surface, which is the graph of a function of x and y. Z equals here phi 1, or we could call it g1 instead of phi. And it is bounded above by a surface which is the graph of a different function, phi 2 of x and y. And if we look at the projection of this region down onto the xy plane, well, we have some plane region D, where the values, which are describing the range of values for x and y for these surfaces. So if we want to evaluate a triple integral over a type 1 region, we can express it as an iterated integral. So let's see how it's done. If we have a function f, which is continuous on the type 1 region E, where z is bounded above and below by functions g1 and g2 of x and y, where x and y lie in D, then the triple integral of that function f over the region E can be evaluated as a triple integral or an iterated integral, where our innermost integral is with respect to z. And our upper and lower limits for z are these functions, g1 and g2 of x and y. So when we evaluate this integral, we're left with a function only in terms of x and y, and whatever we have for that function of x and y, we are then going to integrate over the plane region D, that is the projection of our solid onto the xy plane, as a double integral. Which we know how to evaluate by describing that plane region D as a type 1 or type 2 region. So the other types of bounded solid regions in space are pretty similar. So let's look at what would be considered a type 2 region. We would say a solid region E is called type 2 if it lies between the graphs of two continuous functions of y and z. So that is if we could describe our solid as the set of all points x, y, z in space, where the values of x are bounded above and below by two functions of y and z, and then y and z can take values in some set D within the yz plane. So here D is the projection of our region E onto the yz plane. So we can see that for the region that I've shown here in the notes, we could think about this region as being bounded below in the x direction by the graph of a surface, or a surface which can be considered as the graph of a function of y and z, and it's bounded above in the x direction, that is for larger x values, by the surface which is the graph of a function, say g2 or phi 2. And then the values for y and z could be chosen in this plane region D in the yz plane. If we project our region onto the yz plane, we get this plane region D. So to evaluate a function f, which is continuous over a type 2 region E, where x lies between g1 and g2, and y and z are in some plane region D, we would first integrate our function with respect to x, where x was bounded above and below by these functions g1 and g2 of y and z. And then we would evaluate that resulting function that depends only on y and z as a double integral over this region D, which would be the projection of our solid onto the yz plane. So for our last type of bounded solid region, we would classify it as type 3, and it's said to be type 3 if it lies between the graphs of two continuous functions of x and z. So that is if our solid would be the set of all points x, y, and z, where y is bounded above and below by two functions g1 and g2 of x and z, and x and z are within some region D in the xz plane, which would be the projection of our solid onto the xz plane. So here in this figure, we have a region which could be thought of as being bounded above in the y direction by a function g2 or phi 2, and below by the graph of a function phi 1 or g1 of x and z, where if we project our solid onto the xz plane, our points xz could lie within that region D. So to evaluate the triple integral of a function over a type 3 region, we would first integrate with respect to y, where y is bounded above and below by these functions g1 and g2 of x and z. And then we would evaluate the resulting function of x and z as a double integral over the region D with respect to area, where D is the projection of our solid onto that xz plane. So as an example of this, let's consider an easy solid region to start with. So here we are asked to evaluate the triple integral of z with respect to volume over the region E, where we're told E is the solid region bounded by the planes x equals 0, y equals 0, and z equals 0. So those are the xy, the xz, and the yz planes. And the plane whose equation is 2x plus y plus z is equal to 2. So just like we would for evaluating double integrals over general regions, if we want to evaluate a triple integral over a general region, it often helps to visualize the solid region. So let's think about how we could try to sketch the region of interest here. So here we're told it's the solid region bounded by the coordinate planes. So we're going to be looking at the xy, xz, and yz planes. So here let's visualize our first octant in space. And then the plane 2x plus y plus z equals 2. So to visualize this plane, or the part of this plane that lies in the first octant, that would be bounded by our other planes, let's think about where our intercepts would be. So here to find our x-intercept, I could set y and z equal to 0, and I would have the equation as 2x equals 2, so x would be 1. To find my y-intercept, I could set x and z equal to 0, and I would have y is equal to 2. And to get my z-intercept, if I set x and y equal to 0, the equation of the plane is then z equals 2. So the solid region of interest is going to be the region bounded by my coordinate planes and this plane whose equation was given. So if we visualize our solid region here, well, it's bounded below by the xy plane, on one side by this xz plane, and on the back by the yz plane, and above by this plane whose equation was given as our 2x plus y plus z equals 2. So we could describe this region in any number of ways, as a type 1, type 2, or type 3 region. And for regions that can be described as any type, my personal preference is to always describe them as type 1. I usually like to think about these regions as being bounded above and below by surfaces, which would be the graphs of functions of x and y. So that is, we would project our solid region down onto the xy plane. And let's think about what the projection would look like. So here, our projection of this solid region E onto the xy plane gives us a triangular plane region where our y-intercept, we recall, was 2, our x-intercept was 1, and we're looking at this triangular region in the first quadrant with those intercepts. So this region we could call D, our plane region that we're going to integrate over. And this plane region, D, can be thought of as a type 1 region where x is bounded on the left and right by 0 and 1. And then y is bounded below by the x-axis, y equals 0, and above by this line. And this line is the line whose y-intercept is 2, and it has a slope of -2. So 2 minus 2x would be the equation of this line, which forms the top edge of my plane region D. So let's think about how we could describe our solid region here. So let's start by saying here E could be considered as the set of all points x, y, z, such that our values for z, we said, are bounded below by the xy plane, that is the plane z equals 0, and then it's bounded above by this plane whose equation was 2x plus y plus z equals 2. Or if we solve that equation for z, to think about this as the graph of a function of x and y, we would have 2 minus 2x minus y. So our upper bound for z is that 2 minus 2x minus y. And then the projection of that solid region E onto the xy plane, which we were calling D, can be described as a type 1 plane region, where our values of y are bounded below by the x-axis, that is y equals 0, and above by the line 2 minus 2x. And our x values for this region D, we said could range from 0 up to 1. So the last part of our description for this solid region is where x lies between 0 and 1. Now, once we have the description of our solid region E, we can evaluate a triple integral as an iterated integral. So let's look at this one. We have the triple integral over E of z with respect to volume could be evaluated as an iterated integral, where we would integrate first with respect to z on the range of values from z to 2 minus 2x minus y. Our function was z integrating with respect to z. And whatever we get for that inner integral, we then integrate as a double integral over this plane region D with respect to A. Now, that outer double integral we can express as an iterated integral, like we were doing earlier in our Chapter 5 work. So here, expressing the plane region D as a type 1 region, well, we said our range of x values was from 0 to 1. Our range of y values was from 0 to 2 minus 2x. And then we have this inner integral from 0 to 2 minus 2x minus y of z, first with respect to z. And then for the outer double integral, our differential of area, it would be given in the order here, dy dx. So let's evaluate this iterated integral. So here, starting with the antiderivative with respect to z, we have an antiderivative of 1/2 z squared, which we're evaluating from z equals 0 to 2 minus 2x minus y, and then integrating in the order dy dx. So evaluating z at our upper limit of integration, we have the outer integral from 0 to 1, and then 0 to 2 minus 2x. And we've got a 1/2 of, plugging this in, we have 2 minus 2x minus y squared. And then we subtract what we get when we plug in 0 for z, which is 0. So then we're just integrating this in the order dy dx. So now, let's see how we would need to find our antiderivative with respect to y. So here, there's a few ways that we could handle this. One way that we could approach this would be to make a substitution for our inner function, or another way that we could handle this would be to expand this term. So I'm going to expand, and here I would have the integral from 0 to 1, and then from 0 to 2 minus 2x. And if we expand this expression squared, we have our constant 1/2 out in front times, if I group my x and y terms together, I would have 2 minus 2x squared minus 2 times 2 minus 2x times y, and then plus a y squared in the order dy dx here. Let's find our antiderivative with respect to y. So we have the integral from 0 to 1. And now finding our antiderivative with respect to y, well, this first term, 1/2 times 2 minus 2x quantity squared, is constant with respect to y. So its antiderivative will be that constant, 1/2 2 minus 2x squared times y. Then for our next term, we have a 2 minus 2x, which is a constant, and then a 2y times our 1/2 out front is y to the first. So our antiderivative of that is 1/2 y squared times that constant 2 minus 2x. And then plus our last term, we still have the 1/2 out in front, so we've got 1/2 of y squared. So our antiderivative is then 1/6 y cubed, where we're evaluating from y equals 0 to 2 minus 2x, and then integrating with respect to x. So let's see what we have here. When we evaluate at the value y equals 2 minus 2x, we have this first term is 1/2 of 2 minus 2x quantity cubed. And then when we evaluate the second term, if y is 2 minus 2x, we have minus 1/2 of 2 minus 2x quantity cubed. So these first two terms will cancel each other. And then we're left with just this last term, 1/6 times 2 minus 2x quantity cubed. And then we subtract what we get when we evaluate at 0, which is 0. So writing this out, we're left with the integral from 0 to 1 of 1/6 of 2 minus 2x quantity cubed with respect to x. So in order to evaluate this, well, we could expand this cubic, which starts to get a little bit messy, or we're integrating a composite function here, so we could make use of a substitution. So here, using the substitution, let me use a different color here so this stands out a little more. Let's make the choice of u as our inner function, 2 minus 2x, so that du is negative 2 dx. And then rewriting our integral in terms of u, well, let's see what we have. We have the integral of u cubed, and then we have a leftover factor of 1/6 dx, which leaves us with a negative 1/12 du, rewriting it in terms of u. And then changing our limits of integration, well, let's look at the lower one. If x was equal to 0, then u is 2. And when x is equal to 1, u is 0. So here I have the integral from 2 to 0 of this negative 1/12 u cubed du. So what I might do is first reverse the order of those limits of integration. I usually like the larger value to be on top. So if I change this as the integral from 0 to 2 of u cubed du, then I would have to take the negative of this integral in order to change those limits. So I move from a negative 1/12 to a positive 1/12 out in front. So then our antiderivative gives us a 1/12 times 1/4 u cubed is 1 over 48, and then u to the 4th. evaluated from u equals 0 to 2. So in the last part of our problem, if we evaluate at u equals 2, we have 2 to the 4th, or 16 over 48, which is 1/3. Minus when we evaluate at u equals 0, we get 0. So finally, we're left with a value of 1/3 for this triple integral. So we see that evaluating these can be a bit more tedious than the double integral examples, because now we're working over a solid region, and we have 3 integrals to evaluate in total. But by expressing our region, E, our solid region, as a type 1, 2, or 3 region, and thinking about the projection of our region onto the xy plane as a type 1 region, we can set this up as an iterated integral and use the same approach that we did for double integrals. So in the next part of this section, we'll start to look at integrating over some slightly more complex solid regions in space, and then see how we can use these triple integrals to represent volumes.